Well, hey, Dr. J. Today we're going to learn about implicit differentiation. I didn't have room to write the entire word differentiation, so I abbreviated diff. Um, I did my best to draw a circle freehand without any tools or anything to get the lecture started. So we'll start with implicit differentiation. I'm going to try to get through both of these topics in one video, so let's do this. Not too much small talk. Interesting fact that you might have learned earlier in math is a circle is not a function. So far, everything that we've done, it is impossible to write f of x and have it be the equation of a circle. That's impossible. That cannot be done. All right. So when we take a derivative, or maybe I should say so far, it's going to end today, but so far, to take a derivative, which is what differentiation is, we need a function. That's called an explicit function. For example, something like this, f of x equals x squared. All right, that's definitely not a circle. That's a parabola. So this is called an explicit function. A really easy one. So this is what's called explicit differentiation. Explicit differentiation, we would say the derivative of f of x is 2x, all right? And that's probably one of the easiest derivatives that you've learned in this course. Okay. Now, we can't do that for a circle. And that makes us very sad. Yeah. Especially since a circle is such a fundamental shape in mathematics, in nature. You can't go very far without seeing a circle, right? You see them probably, 100 times a day, you see a circle somewhere. So we would like to be able to do this. So we need a new method. And that new method is called implicit differentiation. Just like everything, we learn a technique, we develop a technique, and then that technique becomes useless, at some point. So let's go ahead and do an example. I'm going to start with the circle. A circle of radius 5 has the equation, I should say centered at the origin. Got to be very careful, centered at the origin. They get a little more complicated if the center is not the origin. Has an equation, or is described by the equation x squared plus y squared equals r squared. So the radius is 5. R equals 5. So we have x squared plus y squared equals 5 squared. Or you could say 5 squared is 25. So notice this is not a function. All right, so how can I find dy dx? And the answer is we're going to use implicit differentiation. Okay. So, let me erase the circle. Maybe I'll draw it again later. It probably won't be as good because it took me a few minutes to do it off camera. It's tough to draw a perfect circle without a tool. So here are the steps for implicit differentiation. Implicit differentiation, we'll call it ID. Implicit differentiation steps. Okay. So step number 1 is to put d dx on both sides of the equation. I usually add some parentheses around the expressions on both sides. So sometimes these equations might already have parentheses. Typically they don't. So you would add some parentheses just to make it very clear that there are 2 separate expressions on each side. All right. So this is sometimes called a differential operator or simply differentiation. Okay. And notice we don't have an F. We don't have an F prime. Now watch how this works. This takes very close eye. We are taking the derivative with respect to x. Okay. So we're going to distribute the derivative to each factor, or each term, sorry, each term. We'll get into factors later in this video. This one only has 1 term, so it's already done. If the right-hand side had more than 1 term, then I would do the same thing on the right-hand side. Okay. So far, so good. The first couple steps are pretty simple. You can, in fact, if you want, in the future, you'll just jump right to this step here. All right, now here's where it gets weird, all right? Or interesting, maybe, is a better word for it. The derivative of x squared is very simple. It's just 2x. Yeah. So that's easy. Yeah. Here's where it gets weird. The derivative of y squared, it is 2y. That is true. But because of the chain rule, y is not a function of x, right? So intuitively, you can think of y as being another function, right? It's a g function or an h or some other function besides the original f. Now, I'm using the term function very loosely. I'm using it in air quotes because this is clearly not a function, right? It's not a function of x. But in the spirit of the chain rule, if you take the derivative of a composition, and you can just think of that as a composition of y is replacing x, it's another variable, you're taking the derivative with respect to x, but this is not a function of x. It's a function of y. It's another function. So we take the derivative, 2y, and then you multiply by the derivative of y with respect to x. So you got to remember to do that. All right. You can't just say 2y and move along. So anytime you approach a y variable, you have to multiply by dy dx to give you that additional factor, the chain rule. Now, when you approach a constant, you get 0, right? So the derivative of any constant is automatically 0. All right, I got to erase that. I need the work. All right, and now we're going to solve for dy dx. In other words, we're going to isolate that. So we want to get that all by itself. So we'll subtract 2x from both sides. We have 0 minus 2x, which is just going to be minus 2x. Then we're going to divide both sides by 2y. And we're going to get dy dx is negative 2x over 2y. And then we'll cancel the 2's. This is technically a negative 1. And so it's just going to be negative 1x over y. I usually don't write 1. I just say negative x over y. That's our derivative. Okay. So we're going to be doing a lot of these today. I don't know, as many as I can get done in the time that we have. So let's sort of summarize what we have so far. We have x squared plus y squared equals 25. We have dy dx now implicitly is negative y over x. Notice why we call it an implicit derivative. It has two variables. So an implicit derivative has typically both variables, x and y. An explicit derivative, explicit, it's kind of nice that it has that in it, is just x. Like all the derivatives we've done in the past. Although it's not always x. I guess we've seen other variables like t and stuff like that. But remember, even if I use the variable t, typically when we take the derivative, we treat it just like x. I probably shouldn't be saying that so soon in this video, but it just keeps popping into my head. All right. And so now, suppose we want to find the tangent line. Remember, we don't always do it, but it is the sort of underlying, purpose of differentiation, of taking a derivative. Find the equation of the tangent line passing through. Now, because this is an implicit derivative, it involves x and y, I have to give you both coordinates. Let's do negative 3 and 4. So try to draw my circle again. The radius was 5, so this is 5, 5, negative 5, negative 5. All right, it's not the most perfect circle, but whatever, it'll do. If I had a tool, I could probably draw it a little easier. So the radius is 5. It's not 25. Remember, this is 5 squared. So the radius is the square root of 25, which is 5. Or you could say r squared is 25. Same thing. So if I say r squared is 25, that's the same thing as saying r is the square root of 25. So just want to make that very clear on the graph. And then I have this point, negative 3 and 4. right here. All right. Now this does have to be a point on the curve. All right. I didn't verify that, but I'll leave that to you. A DIY maybe. If you plug in -3 and 4, it does have to equal 25. I think you could do that just mentally. -3 squared is 9. 4 squared is 16. And when you add those up, you do in fact get 25. So I can't just make up any point that I want. It has to be a point that actually exists on the graph. And so I want the equation of this line here. The tangent line passing through that point. Okay. So you see what we're trying to do here? So now we have to go back and do the slope. So dy dx is -y over x. Oh, sorry, -x over y. Almost said it backwards. All right, so the slope m is -3 over 4, which is 3/4. Seems about right. Look at the graph here. The slope is 3/4. Then I got to find the b. The b is where it crosses the y-axis here, so we'll call that b. Question mark. I don't know what that is. So y equals 3/4 x plus b. Okay. And then we're going to plug in the point, -3 and 4. So we're going to put 4 here for y. Got to put them in the right spot. So this is x and this is y. So y is 4. Hope I'm not in the way here. Let's scoot over a little bit. I'm going to put in -3 for x. Now be careful. It goes in the numerator. I always tell you to be careful. I like to put a little 1 here just to keep that -3 from, so I've seen people cancel the -3s. That would be bad. So now I've got 4 equals -9/4 plus b. There's several ways to do this. I'm going to do it with an LCD. So I'm going to multiply by 4 over 4. So I'm going to get 16/4 equals -9/4 plus b. And then I'm going to add 9/4 to both sides. And my b is 25/4. Which kind of makes sense in the graph. 25/4 is a little bit more than 6. Yeah. It's 6.25 if you wanted to think about it as a decimal. I don't usually use decimals unless it was an application problem, $6.25 or something like that. This is not an application problem, I guess, unless you want it to be an application of the derivative. I just want to get the final answer. So my final answer is y equals 3/4 x plus 25/4. All right, y equals mx plus b. So that is the sort of the classic introduction to implicit differentiation. It's the same lesson that I was taught, 35 years ago when I learned how to do this way back in 1989. So, a little flashback in history. I find it interesting that even in the modern, literature, the textbook that we have, which didn't even exist back in 1989, the same concept is used to introduce implicit differentiation. It's always a circle. Okay. I mean, somebody could make up another example. I'm going to do things that are not circles now. Example 2. Most of these examples are not functions. Some of them actually are functions, but the implicit differentiation just helps us find the derivative a lot easier than trying to rewrite it as a function. It's really just another tool in our toolbox. I'm trying to get the glare off the screen a little bit. Okay, hopefully it's not too bad for you. All right, so here's another example. Let's skip the whole graphing and tangent line. Let's just find dy dx. Let's just practice the steps of implicit differentiation. All right, it's nice and clean. I got a nice big board here so I can go through all the steps. D dx. I would just jump right to this step. Just distribute it to each term. Saves you a little bit of writing. Although technically you put one of these on each side, right? And then you distribute them, so now it's 3. Right. So now you do each one separately. This is a lot like a circle. It's not a function. It definitely doesn't have the same shape as a circle, but it's some sort of weird looking, thing like that. All right, I don't know. I don't want to say what it is because I've never graphed it, but it's similar to a circle in that it's not a function. So that's it, and it has a very similar type of equation. Let's just go ahead and do it. We're not graph. I always say we're not going to graph it, and then I immediately start thinking about, well, what if I did graph it? I could go off on a tangent, but I'm not going to. I'm going to stay focused. We got a lot to do today. So the derivative with respect to x, well, that's just 6x to the 5th. Done. Easy. Now the derivative with respect to x of a y, you take the derivative and then you put dy dx. That's the chain rule. All right. You don't really need the dot, but I like to have the dot to remind me that that's being multiplied. And then the derivative of a constant is 0. And then now you want to isolate dy dx. Okay. So subtract 6x to the 5th from both sides. And divide by 5y to the 4th. Simplify if possible. If it's not possible, you're done. All right, so it's not possible. Sometimes the constants can be simplified. The variables rarely ever can be because notice they're different variables. So it's very rare where you can simplify the variables, but sometimes you get lucky and the constants can reduce or cancel or you get a much simpler result. All right, well, see how quick that is when you see the process straightforward. Did it all in one clean shot. Let's try another one. We got a lot of these to do today. how about this one? 3xy plus 5y equals 4. You've actually seen this equation before, right? Now maybe the numbers were different. They might not have been 3, 5, and 4, but you've seen this equation before. Back at the beginning of the discussion on derivatives, back when we were taking limits, this was one of the problems that we had to solve, and it was not that simple. It took a lot of steps. Not that this is going to be, a walk in the park, but it's going to be easier than the way we did it back in the beginning of the discussion of derivatives. Okay, so you might have a flashback. The answer is going to look slightly different, though, because we're using a different technique, but it still means the same thing. All right, so let's get right into it. I like to put a dot right here just to remind me that those are being multiplied. So my brain kicks into product rule mode. So I've got the derivative of 3x times y, that's going to be a product rule, plus the derivative of 5y equals the derivative of 4. You could just do the right side right now. It's going to be 0. Whenever there's a constant, seems to usually occur on the right-hand side. There's no mathematical reason for that. I think it's just more of a tradition to put the constants on the right-hand side. It's a very traditional way of writing your mathematical expressions, and so that right-hand side ends up being 0 quite often, if not every time. All right, so now we have a product rule. Got to be very careful. So the derivative of the first is 3. Right? Just 3. That's the derivative of the first term, first factor, times the second, y, plus the first, 3x, times the derivative of the second, dy dx. All right, so that's the product rule. Derivative of the first times the second, plus the first times the derivative of the second, plus the derivative of 5y. Now that is not a product rule because the 5 is a constant. So the 5 comes out in front, and then you just multiply by the derivative of y. Well, the derivative of y is dy dx. Now, technically, there's a 1 here. Yeah. The derivative of y, because technically that's y to the first power, is 1, but nobody ever writes the 1. So I've got 3y plus 3x dy dx plus 5 dy dx equals 0. And I need to isolate the dy dx's. Isolate. So I'm going to move the 3y to the other side. I'm going to factor out the dy dx. Bringing down the 3x and the plus 5. Factor it out. Notice there are 2 of them here, but when I write it here, I only write it once. We call that factoring out. Then I'm going to divide by 3x plus 5. And that's your answer. So dy dx is negative 3y over 3x plus 5. There you go. That's my answer. I should mention, if you see this problem in a previous section before we learned this, the answer would have been dy dx equals negative 3 over 3x plus 5 squared. So it would have had a different presentation, but it would have meant the same thing. It would have produced the same result. In an explicit derivative, like we've done in the past, the right-hand side only has numbers and x's, doesn't have any y's. In an implicit derivative, it has this y variable here, and so the presentation of it looks different to the eyes, but it mathematically means the same thing. It gives you the same result. It gives you the slope of the tangent line or the instantaneous rate of change at a particular point. The only difference is implicit requires two inputs, the x and the y, in order to get the result. One thing we're going to do next is a simpler way of writing dy dx. Example 4. 3x squared, oh, not 3x squared, that's the same question. 6x squared plus xy minus y cubed, almost right squared, let's see. Equals 25. Find the equation of the tangent line. How about the slope? Let's just do the slope. I want to keep this moving. Find the slope of the tangent line at the point 2, 1. Yeah, 2, 1. I have to make sure that this point is actually on the graph. Had a little mind melt there for a second. I was questioning whether I needed to change one of the values to a negative, but they're both positive. All right. A little trickier with a 2-variable equation, because with a 1 variable, if it's just x, you only have to be right once, right? With just x. With x and y, both of those values have to, produce the right result here. So just making sure before I have to, recant my statements here. All right, so find the slope of the tangent line. So basically, we can just find y prime. It's just a shorthand notation. Yeah. It's a shorthand notation for dy dx. Okay, so let's go ahead and do it. So we've got d dx of 6x squared plus d dx of xy minus d dx of y cubed equals d dx of 25. And that's going to be 0 again. Yeah, the right-hand side 0 again. All right, this is going to be a little kind of messy here. So The derivative with respect to x of 6x squared. That's just 12x. That's probably the easiest of all of them. Now here it's going to be tricky. This is x times y, so I've got a product rule. I'm getting some parentheses ready for the product rule. So the derivative of the first is 1 times the second, y, plus the first, x, times the derivative of the second, which we're writing as y prime. All right, you could write dy dx, but so much quicker to just write y prime. Minus the derivative of y cubed, which is 3y squared. But again, the chain rule, right? This is a derivative with respect to x, but this is not an x. This is a y. So that's y prime. And then it all equals 0. Your goal is always the same. You want to isolate the y prime. Okay. The parentheses were non-essential. They were just there to make sure I got the product rule correct. I could remove them now. They would be very, I would have to be more careful. They would be essential if this sign out to the left was a minus. Then I would have to be much more careful with removing them. Because this sign to the left is a plus, I can just remove them with like that. And then now I save a little bit of board space here. So I'm going to subtract 12x. I'm also going to subtract 1y. All right. I never do more than 2 maneuvers or 2 manipulations in one step. That's just my strategy. You can do one thing at a time. That's probably the safest way to do math. But if you get, advanced or moderately good at whatever level you're at, then you could do 2 things at a time. I would never, even as an expert in the field, try to do more than 2 things at one time. I have tried doing 3. Right? It's like holding 3 things that are very awkward. You end up dropping one of them. So factor out the y prime. And divide by x minus 3y squared. And that's it. That's your answer. Well, that's the answer for y prime. Okay. We have to find the slope of the tangent line at the point. So the point is xy. So the final answer is my slope, negative 12. I'm going to give myself some more room here. Negative 12 times 2 minus 1 over 2 minus 3 times 1 squared. So that's negative 25 over negative 1. Oh, that's funny. The slope is 25. Total coincidence. Do not memorize that. The slope will not always be the number that's on the right-hand side. It just came out coincidentally. It's because of the point that I picked, which was 2, 1. Maybe to illustrate that it really was a coincidence. If it only happens once, it's a coincidence. If it happens twice, it could still be a coincidence. Typically, if it happens 3, 4, 5 times, then it's probably not a coincidence. There's probably some relationship there or a pattern. It's not just what you call a one-off if it only happens once. Here's another point on the graph. Let's do negative 2. Yeah, I'm not going to do it. I think it'll just make a mess if I do that. Let's try -1 instead of +1. Let's just try another point just to illustrate the coincidence. Let's try -1 for y. So that would make that -1. That would make that +1. Oh man, I'm opening up a can of worms here I probably can't shut. Let's see, 24. Yeah, never mind. You can't pick a new point. You just have to stick with the point that you had. I'm going to end up wasting a bunch of time trying to prove to you that it was a coincidence, and it's a terrible thing for your professor to try to do on camera. Um, Remember, with an explicit function, you only need an x value, right? An implicit function, what I was just about to attempt to do was to find another point that satisfied the equation, and that would have taken me like 20 minutes. So I'm just going to shut up. That is implicit differentiation. Next, we're going to do some applications of implicit differentiation. So this is kind of a wordy application. The cost to produce, and I'm going to say costs plural, 48,280 units. And I don't know what they are, widgets, gidgets, gadgets, whatever, is split between Y dollars in labor costs. So that's the people that work in your factory or whatever. And X dollars in material cost. So this is a new type of cost function, all right? It is not an explicit function, so we won't be using the C. Yeah, C would be explicitly telling us what the cost is. This is an implicit relation, right? Implicit relation. And is given by the relation, right? Or you could say implicitly, right? Implicitly, I hope I spelled it right, by the relation 710 times the cube root of the material cost to the fourth power divided by the labor cost is equal to the number of cell phones that you're making. Or I don't know why I said cell phones, whatever they are. Maybe they are cell phones. Oh, I just said it. I think I have a random word generator that I've been working on for some of the examples. I just got kind of bored calling everything a widget or a gadget or something. So I've been experimenting with this code where I can, have it be a computer or a cell phone or a car, and it will just randomly pop in an item. And if I don't use the random, object generator, then it just be a unit or a widget or a gadget or a gizmo or whatever. So what the hell? I decided that I'm going to call these cell phones. All right. So the cost to produce these cell phones is given by this relation. Right. It's not an explicit function. It requires two inputs, an x and a y. And I'm not going to try to guess this time. I'm going to use my predetermined numbers. Like last time, it was 2 and 1. And once you have those predetermined numbers, those are the numbers you have to use. Okay. So first, I'm going to do a couple of things. Find dy dx. So that's the whole point of this lesson. And then find the rate at which labor costs are changing with respect to WRT material costs when y is equal to, or x is equal to 5,120. I'm not trying to make these up, and 2,600. So again, if I tried to make these numbers up, the odds of them actually satisfying the equation would be very, very slim, right? You almost saw me do it in example 4 at the end, because I tried to embellish the example with another sort of, takeaway. But whatever numbers you have, those are the numbers you better stick with. The chances of you being right are pretty slim. All right, this is a kind of a wordy problem, so I'm going to have to erase the word. Basically, you can just read it, make sure you understand what the question is asking, and then now you just need the equation. So 710, I'm going to rewrite this as x to the 4/3 times, or over y to the 1/3 equals 48,280. So I'm going to rewrite the equation first. Let's try to simplify this a little bit. Let's divide both sides by 710 and hope I don't get a decimal. If you do, so what? It's an application problem. You can handle decimals. 48,280 divided by 710. Let me try that again. 48,280 divided by 710. Oh, good. Whew. I just said, it's okay if you get a decimal, don't worry about it. But then when I got one, I panicked. It's not a decimal. I typed something in wrong. So there you go. 68. Nice. All right. Decimals are okay. They might happen in word problems, but I just was hoping it wouldn't happen today. So now I'm going to rewrite this as x to the 4/3 times y to the negative 1/3. And I'm going to use implicit differentiation. All right, so here's my rewritten. The y is in the denominator, so it becomes negative. The x is in the numerator. And now I'm going to do my derivative. So I'm going to take the derivative of both sides. The right side's just going to become 0. That's easy. Now we'll do the product rule. The derivative of the x factor is 4/3 x to the 1/3. Right, times the y factor, y to the negative 1/3, plus the x factor, x to the 4/3, times the derivative of the y factor. So the derivative is going to be negative 1/3. Yeah, bring the negative 1/3 down in front. Subtract 1, so that becomes y to the negative 4/3. And then y prime. All right. So this is 4x to the 1/3 over 3y to the 1/3 minus, so I'm going to bring this 1/3 out, 1x to the 4/3 over 3y to the 4/3, y prime equals 0. I'm going to write down these two numbers, so I'm going to need them later. All right. Actually, I wrote them down backwards. The y is 5120. I'm glad I caught that. And the x is 2600. Man. A lot of little things you got to keep track of here. All right, so remember, my goal is to isolate the y prime. Okay, so I'm going to move all this stuff over to that side. Move that over here. Cancel those guys. So now I've got negative 1x to the 4/3 over 3y to the 4/3 y prime equals negative 4x to the 1/3 over 3y to the 1/3. Now watch this trick. This is a technique that's long overdue. When I have a fraction divided by a fraction, I can just multiply by the reciprocal. So I'm going to put the 3y 4/3 on the top. And I'm going to put the negative 1x 4/3 on the bottom. You don't really have to write the 1, but I already wrote it, so I figured I might as well just keep writing it. And then now watch. You've seen this before in algebra. It probably wasn't this complicated, but you've seen the basic concept. You multiply by the reciprocal, and all of this stuff cancels, and now you've got your y prime isolated. So now y prime is, I'm just going to copy the whole thing, negative 4x to the 1/3 over 3y to the 1/3 times 3y to the 4/3 over negative 1x to the 4/3. So I can cancel the 3's. I can cancel the negatives. And I can subtract the powers. When you subtract, you do the numerator power minus the denominator power. So be very careful with the order that you subtract. You can rearrange them after you've subtracted, but it's better to do it in the right order and then, manipulate it afterwards than try to, I call that jumping the shark, if you fall in the water and so 1/3 minus 4/3 is negative 1. And 4/3 minus 1/3 is positive 1. So the derivative is 4y over x. That's your dy dx. All right, it's y prime. Same thing as dy dx. Whew, that was tough. Yeah. And I haven't even plugged in the numbers yet. Now, if this thing was horribly complicated, then I would be griefing on plugging in these numbers, but it's not going to be that bad. We can plug it in with our calculator. So 4 times, and I'm glad I wrote this down carefully. So the labor is $5,120. The material is $2,600. I almost got that backwards. So the labor is Y and the material is X. So plug them in. Yeah, plug in. And you're going to get dy dx is 4 times 5,120 over 2,600. Four times 5,120. So it's 20,480 divided by 2,600. I'm writing it down in case I screw it up. $7.87. So I'm rounding that to 88 cents. All right, so what does this mean? This means that labor costs are increasing by this much, $7.88 for every dollar spent in materials. Which kind of makes sense. Yeah. I mean, you know, labor, the work that the people are doing is more expensive and in fact increasing. For every dollar that you spend on material, you're adding an additional $7.88. So you think of it like a slope, right? The labor costs are increasing, which is good for the workers. Yeah, hopefully they're passing the cost on to the. I mean, you're assuming that labor cost means that your employees are getting paid this much money. Some companies really, you've probably seen the news, big corporations that try to, bring the labor costs down because when the boss man, sees this number, they go, no, we don't want to pay $7 in labor for every dollar of material. They want to bring that cost down, and the way to do that is to smash labor unions and to smash the workers and to try to keep minimum wage down and try to keep you, working night and day and night. All right. So this is your way to stick it to the man and learn calculus, and then get out of the cycle of economic hardship, which I don't know if it ever ends, but you could certainly get an advantage by becoming educated, and that's my goal as an instructor to teach you what you need to make you successful. So I only have one example of this today, so that's going to have to do it for implicit differentiation. The next topic is related rates. These are all bundled together into the same section, the same lesson, the same types of techniques. Related rates begins as with a circle again. Yeah, we start with a circle. Let A be the area of a circle of radius r. So again, think back to the circle that I drew, but think about the area as being the inside of the circle. So area is sort of, if you painted the inside of the circle or filled it in, that would be the area. Okay? If the radius is increasing at a rate of 2 inches per second, how fast or at what rate is the area increasing? When the radius reaches 6 inches. So let me just sort of draw a sequence of circles. So you have this, and then this, and then this, and so on and so forth. So this would be, say, radius is 1, radius is 2, radius is 3. And so what's happening is the area is getting larger and larger and larger. And so we want to know how fast, at what rate is the area increasing. That's called dA dt. So related rates, we use t for time, and the time is going to be specified in the question. So in this question, it is specified as seconds. So t is for time. It's not always going to be seconds. T is the seconds in this particular example. Generally, it just means time. Okay. I'm not going to try to trick you. I'll always tell you in the question what unit of time we're using. And I also don't change units in the middle of a problem. So whatever units they are, that's the units they'll remain in that problem. Common units are seconds, minutes, hours, days, weeks, months, and years. Sort of common units of measuring time. Okay, let's go ahead and do it, right? First, we need to remember the area of a circle formula. It just says let A be the area of a circle. You do need to know the formula. It's pi r squared. So the derivative is 2 pi r. Take the 2, bring it down in front. Yeah. But because r is not a t, right? Notice there's no t in this equation. You have to use the chain rule and multiply by dr dt. So dr dt is the rate at which the radius is increasing. The radius is r, and it is increasing at a rate of 2 inches per second. So we're going to replace that with 2. And then the radius is reaching 6 inches. So we're going to replace that with 6. pi is a number, not a variable. So we got to be really careful with that. Don't, take the derivative of pi like as if it was a variable. It's just a constant. So this is going to be 24 pi. 6 times 2 times 2. Maybe have a pi button on here. Yep, right here. We got a pi button right there. So that's going to be 75.398. For this one, it's not money, so I'm just going to round it to 1 decimal. Write it over here. dA dt is 75.4 square inches per second. So yeah, because it's not money, I'm just doing 1 decimal. I mean, I could even do no decimals, but this question asks for 1 decimal place, the 10th. So we did 75.4 because the 39 rounds up to 0.4. So that's how fast, that's the rate at which the area is increasing. It's a lot, yeah? Look at the radius is only getting larger by 2 inches every second. You think of this like an animation, right? Every second, the circle's getting larger and larger and larger and larger. But the area, the amount of space inside of the circle is growing at a much larger rate, 75 square inches every second. So every second, there's 75 more square inches of space in that circle. Again, implicit differentiation, the very first example, the classic example is a circle, in particular the tangent line of a circle. For related rates, we're using a new variable, t. So we're measuring the rate with respect to time. And the classic example is the circle is getting larger. Okay. So now we'll move on to some business applications of the related rates. The most common application, in fact, the one that we're going to focus on in this lesson is price and demand. Over time. So what we're going to be doing is we're going to be taking the derivative with respect to time, WRT. So typically time would be like in the last example, it was seconds. With money, you have to wait longer than a second for stuff to happen. A day, a week, a month, a year. Those are the most common time intervals that we'll have. So let's just start with an example. Example 7. So a company sells widgets. Sorry, I'm back to just generic names for things, and has found that the number of units they can sell depends on the price. Yeah, we've seen this before. And so the equation is the number of units X is $7,000 divided by, or 7,000, not necessarily dollars, divided by the square root of 4p plus 1. So p is the price, the number of units X, called the demand, is based on the price p. Okay. which seems obvious, right? We've talked about this before. Now, this type of relationship is not quite obvious. The ones that we've seen were much more simple, straight line. This one's a little bit more exotic, so I've sort of prefabricated it for you here. Due to inflation, so this is where the time factor comes in. The price has been increased. So the price is increasing at a rate of 15 cents per month. So that's our time factor. Find the rate at which the revenue is changing when P is $210. So I'm giving you a price, and I want to know at that particular price point, how fast is the revenue changing? All right. All right. So what do we have? We have revenue is P times X. Yeah. And this is X. So revenue is going to be P times this whole formula, 7,000 times the square root of 4P plus 1, which is equal to 7,000P over the square root of 4P plus 1. All right, so that's revenue as a function of price or as an equation of price. In this section, I don't use the function notation because we are using the alternative form, the implicit form of the derivative, and we're going to be taking the derivative with respect to t. So let's go ahead and do it. Let's take the derivative with respect to time. So the derivative with respect to time of both sides. Sorry about that. So the derivative with respect to time on both sides. I might want to save this. This is an important feature. It tells me how many units we're selling at that price. So I might need this, 7,000. I'm going to erase it for a moment, but save it over here. Okay. So the derivative with respect to time of the revenue is just called dr dt. That's derivative of revenue. That's actually what we're looking for. Find the rate at which the revenue is changing. So that's what this is here. This is the rate at which revenue is changing with respect to time. It's a function of P. So we're going to plug in 210 at the end when we're done. All right. Now, let's go ahead and do it. This is pretty complicated because we have a quotient rule here. So we have the derivative of the top, which is going to be 7,000. Yeah. dp dt. The derivative of the top is 7,000 times the derivative of P, which is dp dt, times the bottom, 4p plus 1 square root minus the top, 7,000p, times the derivative of the bottom. Now, the derivative of the bottom is going to be messy. In fact, I wish I had more space. Let's just move this over a little bit. 7,000 dp dt times the square root of 4p plus 1 minus 7,000p times, now I got to be careful here, the derivative of the denominator is going to be 1/2 4p plus 1 to the negative 1/2 times the derivative of the inside, which is 4 dp dt. That's that implicit differentiation that we have been focusing on in this lecture. I should also save this 15 cents here. I don't want to lose it. dp dt, the rate at which the price is increasing, is 15 cents, which is a decimal 0.15. So I better save that too. I should probably also save this. P is 210. So these are all my saves for later over here. All right, so we got the derivative of revenue with respect to time. So can we clean this up a little bit? I think we can. Let's do 7,000 square root 4p plus 1. That one really doesn't get much better. dp dt, which is going to be 15 cents in a minute. Minus, let's clean this up a little bit. 1/2 and 4, that simplifies to become 2. And then 2 times 7,000 will be 14,000 p. And then I've got a negative 1/2, so I could send that down to the denominator and write it as a square root. And then put my dp dt again on the outside. All right, so I could even do this. I could even put an extra set of brackets here and put the dp dt out, since I've got 2 of them. All right. And then there's one thing I almost forgot. It just occurred to me. I've got to divide this all by the denominator squared, which will just cancel the square root. Almost totally blew it there. This video has already gone on quite a long time, but hang in there because I'm not filming another part. This is a one and done video here, one and done lesson. So I mean, my attempt was to make it simple. I don't know how successful I was at that, but nonetheless, you are now going to plug everything in. So I've got dr dt, the derivative of revenue with respect to time. I've got all these things. I've got my P is 210, and I've got my dp dt is 15 cents. All right. I don't need the X. The X is how many of these things I would be selling. I might be curious and solve that for that later, but I don't really need X right now. I just need P and dp dt. All right, so plug everything in. So I've got 7,000 times the square root. Why don't I just do this on my calculator? What is 4p plus 1 when P is 210. So 210 times 4, 840 plus 1. So that's the square root of 841 minus 14,000 times 210. 14,000 times $210. That's how much we're selling each widget for. That's 2,940,000 over the square root of 841 times 15 cents. That's this dp dt here. All over. Now this one doesn't have the square root anymore. It's just 841. So it's all numbers now. And this number tells me the rate at which revenue is changing. So I don't know where to start. I guess square root of 841, I guess. Oh, nice. I couldn't have planned that any better. Square root of 841 is 29. So I've got 7,000 times 29 minus 2,940,000 over 29 times 15 cents, all divided by 841. All right, I guess I'm going to work 7,000 times 29. And if you don't mind, I'm just going to do that now. 7,000 times 29 is 203,000. That's going to make the rest of this a lot easier. So I've got 2,940,000 divided by 29. And then make that negative. And then add 203,000. And then multiply that times 15 cents. And then divide it by 841. So my revenue is changing. So DRDT at a rate of $18.12 per unit. Not per unit, per, what was this? Month? Month. You got to make sure you read the question to figure out what your time is an increment of. And again, I'm not going to try to trick you. Whatever it says in the problem, that's what time is. Last example, it was seconds. Now it's months. Could be weeks. Could be years. Could even be days. All right. So there we go. Revenue is increasing. It's positive. So it's increasing at a rate of $18.12 per month. When the price is $210 per unit or per widget. And then the demand is, if you're curious, remember this is 7,000 divided by the square root of 841, which turned out to be 29. So 7,000 divided by 29, just out of curiosity, I did this. You have to round to the nearest unit. So this particular company would sell 241 units or widgets at $210 per widget, and the revenue would be increasing at a rate of $18.12 per unit. So we only have time for one more example, and then we will be done with our lesson on implicit differentiation and related rates. The next example is given in two parts. There's an equation for the demand and the price. So a store sells, I don't know, what was the store selling? Coffee makers. I don't know. I can't think of anything else. For $P each. The relationship between the number of units sold, called the demand, is given by, now this one's not quite as simple, it's given as an equation. So it's given by an equation. All right, it's not a simple function, it's a relationship between the number of units sold and the price P. Okay. The price T months from now can be predicted by the equation P equals 47 plus 0.3 times the square root of T cubed. So as we know, as time goes on, the product is going to get older and the price may go down, right? It's going to end up on sale at some point. And so this formula, again, it's not intuitive. It's not something you would memorize. It's something that's been manufactured ahead of time, predicts the price in the future. Calculate the rate of change of demand 24 months from now. So everything starts right now, right? So we're doing this analysis now. That's time equals 0. That's the 0 month, right? You could just plug in 0 if you're curious. Might as well. So right now, the price of the coffee maker is $47. Right? You plug in 0, this whole term turns to 0. And then as time goes by, the price will change over time. It looks like the price will actually go up. That's interesting. We'll find that out as we go. Okay. All right, so let's get into this. I don't need all these words here. We're going to take the derivative with respect to time of 3px plus the derivative with respect to time of 2x, and then the derivative with respect to time of 32,969. Okay, so derivative with respect to time of 3px, that's going to be 3 this is a product, 3p, so the derivative of 3p is just 3 times dp dt times x plus 3p times the derivative of x, dx dt, plus 2 times the derivative of x, dx dt. The question is asking us for the rate of change of demand. Oh, I forgot to finish this. The right-hand side's 0. I paused for a second, forgot to do that. So that's equal to 0. So the rate of change of demand is dx dt. It's good to pause and think about what it is you're actually trying to solve for. So this is what we're trying to solve for. You look at this messy equation, you might look, what are you actually trying to do here? So just pause, think, read, and this is what we're solving for. All right. We know this. This can be obtained by using the price demand function. I think I initially meant for the price to go down over time. I'm not going to change the problem now, so perhaps this coffee maker in the next couple months, maybe we're opening it up, selling it at a lower price, and then we'll crank up the price over time. I don't know. I don't sell coffee makers, but my initial instinct was that over time the price would go down, which is kind of intuitively what does happen. But, this is a model. A model is not perfect, but once you have the model, you should follow the model. So 24 months from now, we want to know the demand, right? And the demand is going to be dp dt. Well, we want to know how the demand is changing 24 months from now. So the derivative of the price is 0. Yeah, derivative of 47 is 0. Plus 0.3, and then this is one of those square root with a power, so that's t to the 3/2. So that's 3/2 t to the 1/2. So that's going to be 0.9 over 2 square root of t, which is 0.45 square root of t. So this is our rate at which the price is changing. 24 months from now, that's our value of t. So our value of t, we're looking for dp dt. dp dt, if we plug in 24, is going to be 0.45 times the square root of 24, sorry. 24 months. It's not going to be pretty. So we got the square root of 24. I was hoping it was the square root of 25 months, would have been nicer. But square root of 24 months times 0.45. That gives me 2.2045. Probably just get away with 2.2. All right, so I've kind of left this problem kind of hanging here. I was trying to clean it up a little bit, so now I can plug 2.2 into here. So I've got 3 times 2.2 x plus 3p dx dt plus 2 dx dt equals 0. I probably could have done this a few minutes ago, but I didn't know what dp dt was. So I did a little scratch work to figure out what dp dt is, the change in price over time. It's 2.2, which tells me the price is actually going up. Yeah, price is going up. So that's going to be 6.6x plus 3p. I'm going to go ahead and factor out the dx dt. And you're going to solve this by moving the 6.6x over to the other side. And then dividing by 3p plus 2. So that is your answer without a value plugged into it. The rate of change in demand is negative 6.6x over 3p plus 2. So all of that work was to discover the related rate and how the demand is related to time. And over time, in 24 months, that's 2 years, this will predict the change in demand, how demand is changing. Now, here's the problem with this. This is not a number, right? And the boss doesn't want to hear a formula for an answer. The boss wants a number, right? Tell them how they want a decimal or maybe even a whole number. We'll give them a whole number, right? Because it's a unit. You can't say 5.5 units. It's 6 units or 12 units or whatever. So we want a number for this. So we need to go back and figure out what these inputs are. But remember, we have a formula. P is the easy one. P was $47 plus 0.03 times the square root of 24 cubed. Yeah, remember, 24 months was T. We already had this formula. I just copied it back down again. So we've got 24 cubed. That's 13,824. Then we have the square root of that. That's 117.57. Then we got to multiply that by 0.3. Coffee maker just got really expensive. Yeah. And then plus the original $47 cost. I don't know what kind of coffee maker this is. I'm rounding to the nearest cent. So this is the price of the coffee maker in 24 months. So I don't know what kind of company this is. I don't know what kind of coffee makers these are, but when they first were released, they were $47. 2 years later, the price has gone up to $82. Not every word problem is a realistic situation, but I don't know. I mean, maybe the price did go up. Maybe there was less demand. I don't know. I'm gonna find out what happens to the demand. Intuitively, if the price goes up, the demand will go down. Right? That's intuition of basic common sense. But I don't know. There's formulas for things that are not common sense. So now we have a P. So this P can get plugged in here. We don't have an X yet. So we've got 3px plus 2x equals 32,969. We have a price, 82.27. And we have an x that we can solve for. This looks much more complicated than it is. We're just going to add these together. So we got 82.27 times 3 plus 2 gives me 248.82x equals 32,969. Divide both sides by 248.82. And there's your x. $132.5. I guess I'll round up to 133 units. Although that does throw off the answer a little bit, but that's okay. I have a tolerance for the answer. This is a heck of a problem, but it is the last one. So, you got to put a lot of time into the last one. So dx dt, 24 months. The old-fashioned way to write this is you put a little bar and you write t equals 24. It's just a little reminder of how many months have gone by. And now we plug everything in. We've got 133 units. The price is $82.27. And just plug this into your calculator and interpret the result. So let's see. I rounded this already. You could leave it alone if you want. It's up to you. I already rounded it, so I'm going to go with the rounded number. 133 times 6.6 negative. So I've got negative 877.8. Should probably do the denominator as well. 82.27 times 3 plus 2 is 248.81 or 0.8. Divide those. And I get approximately 3.5. It is 3.527, which we have to round to 4. I know that seems weird. It's not even close to, it's almost 4, but not really. But I do want you to round it. And it is an X, so you can't have a half an X. Not when we're talking about a coffee maker. You can't sell half a coffee maker. So that's the answer. The answer is 4. And so what does this mean? All right, let's just sort of summarize what we just resulted. 24 months from now, the price of a coffee maker is $82.27. The demand is 133 units. Right, so you're only going to sell 133 of them. And it is decreasing. So people are buying less coffee makers at a rate of 4 units, not dollars, per month. So every month, it's probably because the price is too high. I mean, I've never sold coffee makers or anything, but I mean, if the demand is going down, you're selling 4 less coffee makers per month, the price is too high. Right? And so the number of units then is going to go down. So next month, I'm only going to sell 129 units, right? 4 less than this. And so on and so on and so forth until people just stop buying the coffee makers. And then what do? You make a new coffee maker and you start the whole process over again. All right. Okay, well, you hung in there, but by doing this all in one video, we do not have to have a part two. So we have completed the section on implicit differentiation and related rates. And so that's the end, my friends. Until we meet again, I'm Dr. Jordan, and I'll see you on the internet.